Hello there. We will now work through the Chapter 12 review worksheet. I encourage you to, as we go through the worksheet, to kind of pause the video and give the problem a try, and then to check your work. So let's look at the first context here. So this one says at Camp Barker, there are over 800 campers each week in the summer. At the end of each day, the campers get to choose one of three activities to do. They can choose either the ropes course, the water slide, or a horse ride. One day it is claimed that 55% will choose the ropes course, 32% will choose the water slide, and 13% will choose the horse ride. A camp counselor decides to test this claim. She takes a simple random sample of 70 of the campers and finds that 36 of them would choose the ropes course, 17 would choose the water slide, and 17 would choose the horse ride. She then performs a test of significance. So first thing to notice here is that these are categorical variables. Okay, this is certainly not quantitative. Okay, and we have claims about the categorical variable, claims about the categories, and then we have a sample that tests those claims. And so it is claimed that, you know, the proportion for the ropes course is 55%, and the proportion for the water slide is 32%. And the proportion for the horse ride is 13%, okay? And so those are in essence our claim. And then our observed counts, we take a sample and we observe some counts. And so for the ropes course, our observed count is 75, 36 wants the ropes course, and we find that 17 want the water slide, 17, and then the horse ride is 17. So are these proportionately so different from the claim proportions that it would cause us to reject these proportions? And this is what is known as a chi-square goodness of fit. In other words, do our observed counts fit with the hypothesized proportions? So let's talk about the questions in that regard. Number one, what is the name of this type of inference? And so here we go. And so that would be a chi-squared goodness of fit test. All right, so then number two, what are the hypotheses? All right, so your null hypothesis is going to be just whatever the claim proportions are. So those are the claim proportions. The alternative in a chi-squared goodness of fit is always going to be that at least one of the above proportions is wrong. So in a goodness of fit test, you just write down what the claim proportions are, and then the alternative is just at least one of the proportions wrong, and you have to define what this notation is. So the P sub R is the proportion of all the campers that would want to do the ropes course, and then P sub W is the portion of all the campers that would want to do the water slide, and P sub H is all the campers that would want to do the horse ride. So you have to define your proportions. That's how you do your hypotheses in a goodness of fit test. And so then it asks us to verify the assumption. So we in essence sort of have to send, even though we don't have normality in this chapter. So certainly randomness is always a condition. It says an SRS was taken, so random condition is met. All right, there must be at least 700 campers for our little n to be less than 0.1 times our big N. It says there's over 800. So anyway, so we've had both of those conditions for a while now. And then all the expected counts are greater than 5. So that we don't have normality. Do not say normality in, sections 1 and 2 of chapter 12, okay? In chi-squared, it's just the expected counts are greater than 5, and there's what the expected counts are. And how did we get those expected counts? The way you get the expected counts is by taking your sample size, which in this case is 70, and multiplying it times each of the proportions. And that's how many we would expect in our sample in the long run to do that. But let me show you. All right, so, okay, and I'll show you that in a second. So then find the test statistic, the degrees of freedom, and the p-value. All right, the degrees of freedom is the number of categories minus 1 for a chi-square goodness of fit. Okay, number of categories minus 1. So there's 3 categories, so the degrees of freedom is 2. And so let me show you how to get your mechanics. And so this is what we're going to do. All right, with a goodness of fit, we're going to go to our lists. And so we're going to hit the stat button. So we hit the stat button and hit edit and go to our list. Let me clear these lists out. Clear down arrow, clear down arrow. And in list 1, I'm going to put the observed counts. The observed counts are 36, 17, and 17. Those are our sample values, 36 and 17 and 17. Our expected counts go in list 2. So this is how you do that. All right, so first of all, for the ropes course, it's 55% of 70. So you would just take 70 times 0.55, just like that. That's how you get your expected counts, the sample size times the proportion. It's like that. So for the second one, which is the water slide, it would be 70 times 0.32, right there. And then for the third one, for the horse ride, it'd be 70 times 0.13, boom. That's how you get those expected counts. Now you must list the expected counts there. When in your conditions, in your assumptions, you must list them. That's important. And so then now to do your mechanics, you would just go stat, you would go tests, and you would scroll down to goodness of fit test right there, goodness of fit, GOF, hit enter, list 1 and list 2, your degrees of freedom, number of categories -1 for goodness of fit. So that would be 2 here. You go calculate. And so there's our chi-square test statistic, our p-value, and our degrees of freedom. And here's the contributing parts, the chi-squared, in the order that we listed them in. And that would be, so that's the contributing part for the ropes course. That's the contributing part for the water slide. And that's the contributing part to the horse ride, which that would be the biggest contributor to the chi-squared. So I wrote it down. You don't have to show your work here. I kind of encourage you to do that because that's how the contributed parts are calculated. And so, and that is just your chi-squared test statistic, how it is calculated. If you're doing it by hand, it's just going to be the observed count minus the expected count squared over the expected. Observed minus expected squared over the expected. And you do that for all of them, in this case, all 3 of them, and then add them up. And that's how you get your chi-squared. And so that's what I did there. So you notice if you go back to your list, stat and edit. So for the first cell, for the ropes course, it'd be 36 minus 38.5 divided by 38.5. For the second one, 17 minus 22.4 over that. And then there's it is for the third one, 17 minus 9.1 over 9.1. So that's doing it by hand, but you just have to show those 3 numbers there. So number 5 says draw a conclusion with the p-value. And so what you would say, and we've been doing this conclusion for a while now, if the p-value is low, you reject the null. Okay. In this case, it's below 0.05. So I reject the null. There's convincing evidence that, and then you restate the alternative. There's convincing evidence that at least one of the claim proportions about camp activity is wrong. And that's how you do it. If your p-value is above 0.05, you'd say you do not reject the null, that you do not have convincing evidence that, and then you restate the alternative. And then, okay, so that's that. Then it says do a follow-up analysis. Follow-up analysis means look at these contributing parts, which, like I said, your calculator does tell you. And if you want to look at them, we just looked at them, but it stores them in a list. And so if you want to highlight the top of list 3 like that, and then go second list and go to CNTRB, that's contributing parts to chi-squared. You hit enter, and those are the contributing parts to the chi-squared. And you would notice that it's the 3rd category that's contributing the most, and that would be the horseback riding. So that's what I said. So the horseback riding category, which is that, contributes the most to the chi-squared test stat. So there you go. That is how you do that. All right, the next problem. So the next problem says this, and this one you'll notice we're given a 2A table. So whenever you're given a 2A table like this, you ought to think we have a chi-squared test of association or maybe a chi-squared test of homogeneity. So this one says, Frank works at a golf course. He wishes to see if there's an association between how good a golfer is, their level of play, and whether they decide to ride a cart or walk the course. The course has over 2,000 golfers each week. He takes a random sample of 175 golfers one week and categorizes them as being low level, medium level, or high level golfer. He also notes whether they ride a cart or walk. The results are shown in the table below. He wishes to perform a test of significance to see if there's evidence of an association. So is there an association between the level of golfer and whether or not they ride a cart? In other words, if I told you their level of golfer, would that change the proportion of whether they'd ride a cart? Well, if you look at it, on this thing. The low level of golfer appears to be much more likely to ride a cart, and the high level of golfer tends to be more likely to walk the course. Okay, so what is the name of this type of inference? The key word here, well, first of all, you notice it's we have in essence two categorical variables. Okay, it's category. These numbers are counts in categories, and that means it's, when you're doing a test, it's time for chi-squared. Okay, chi-squared, and in this case, it asks, is there an association? So it's a chi-squared test of association. And of course, the other giveaway there is the fact that it's just one sample, not two samples. If it was two samples, okay, it'd be a chi-squared test of homogeneity. Okay, so and in which case it would ask you, is there a difference in these two populations? But anyway, it's one sample and it says, is there an association between these two categorical variables? So the name, what is the name of the type of inference they should do? And there it is, the chi-squared test of association, or the chi-squared test of independence. All right, so then it says, what are your hypotheses? All right, so your null hypothesis in a test of association is always that there's no association between the two variables, level of golfer and whether they ride a cart or walk. The alternative is always going to be that there is an association, okay? Of course, the synonyms of this, it could be that there's no relationship or there's no correlation, okay? Or that they, in fact, they are independent. The other way you could say this, the null hypothesis is that the level of golfer and riding a cart are independent. And the alternative would be that they're not independent. But anyway, so this is good there. All right, so then it says verify the assumptions. Okay, well, here we go. So assumptions, it says a random sample was taken, so random conditions met. That's always a condition. It's always our most important condition. Our sample size was 175 here, so we multiply that by 10, and we would say there must be at least 1,750 golfers this week for our sample size to be less than 10% of our population size. And all the expected counts are greater than 5. What did I forget to do? You have to, I would have gotten partially correct here because I did not write down what the expected counts are. How do we find them? Okay, this is what we're going to do. So we are going to enter this into a matrix. Whenever you're given a 2x2 table and you have to do a chi-squared, you have to enter into a matrix. So here we go. And so let me quit out of this. So the matrix menu is right below the math button, right above the x to the -1 button. So if I go second x to -1, that takes me to matrix, and I'm going to arrow over to edit matrix A. And in this case, this has 2 rows and 3 columns. So I will say 2, enter, 3, enter. And then I just start entering these numbers, 48 and 30 and 15 and 18 and 24 and 40. Right like that. There we go. And then all we've got to do to get our mechanics and to get our expected, this will calculate my expected values for me automatically. So what we got to do is we go stat, we go test, and we scroll down to chi-squared test. Right there. Chi-squared. That's a chi, not an x, by the way. All right, chi-squared test, enter. Observed is in A, expected is in B. And I hit calculate, and that tells me my 3 numbers, my test statistic, my p-value, and my degrees of freedom. All right, but, okay, so that's what I wrote down. That's what I wrote down right there. Test statistic, degrees of freedom, p-value, okay, right there. But you must write the expected counts here. Well, how can you see what the expected counts are? By looking at matrix B. And so what I'm going to do is I'm going to go second matrix, and the easiest way to do it, I think, is to edit matrix B, go edit and go down to edit matrix B. The calculator put those in there automatically. So edit matrix B. Let me make sure. I'm going to do that again because I don't know if you can see that. So second matrix and go to edit matrix B, boom, and there they are. And so you have to write all those down and don't round them to the nearest integer. So for my expected counts, so this would be 35.074 and 30.926 and 28.697 and 25.303 and 29.229 and 25.771. There they are. Those are my expected counts. Remember to write down your expected counts. I'm sorry, I forgot. So so that is that. Now, by the way, you say, how were those calculated? And I explained that in the 12.2 video. calculating that by hand. The expected counts for each cell was calculated by multiplying each cell's row total times its column total over its table total. Okay, and so that is how, so for low and riding a cart, that's what that number is right there. And so that's doing it by hand. Okay, and so we've got our test statistic, degrees of freedom, p-value. And so now draw a conclusion with your p-value number 11. So our conclusion number 11 with our p-value, this p-value is less than 0.05. So I reject the null hypothesis, just like the last one. There is convincing evidence that, and then you restate the alternative. There is an association between the level of golf and riding a cart. So as we suspected when we looked at the two-way table, it is statistically significant that it appears that the lower level is much more likely to ride a cart. A higher level is much more likely to walk the course. So that would make sense. That would be the case. All right, number 12 asks us to interpret the p-value. Now, what we just did here was draw a conclusion with the p-value. Interpreting the p-value is describing it as a probability, as a conditional probability. And so that's what I'll do. It's a p-value is the probability of getting a sample value this unusual, assuming the null hypothesis is true. So if we assume the null hypothesis is true, in other words, if we assume there's no association between the level of golf and taking a cart or not, the probability of getting sample values this unusual is, and then the p-value, 3.5907 times 10 to the negative 6. In other words, 0.0000035,907. In other words, approximately 0. In other words, it's extremely unlikely to happen by sampling variability. And then we have the last context here, and that would be a linear regression where we're given the computer printout. This is the most common way that linear regression problems are given to you. So this one says, a doctor wishes to see if there's a relationship between the number of hours that college students sleep at night, the explanatory variable, and the score they get on a memory test, which that would be the response variable. So that would be the response variable. Okay. He takes a simple random sample of 50 college students from a local university. There are over 7,000 students at this university. He performs a regression analysis and gets a computer printout shown below. Assume the conditions for inference are met. So you have to be able to read this computer printout, as I've told you before. And so the first thing to do is to realize this first number here, the coefficient of constant, that is the constant of the linear equation. That's your y-intercept, that's A. Coefficient, and here's the x variable, the explanatory variable is always there, okay? And so that is our B, okay? These numbers next to A, we'll never use them. These numbers next to B here are important to us now, okay? That's the standard error of the slope, that's our t-test statistic, that's our p-value. There's S, R squared, we'll never use R squared adjusted, so you go like that. All right, so what are the hypotheses of this test? So in essence, we're asking the question, is there a relationship between the amount of time a student sleeps and the score they get on this memory test? That's what we're asking. Well, our null hypothesis for a linear regression t-test is that beta is equal to 0. In other words, that there is no relationship between the sleep time and the memory test score. That is, in essence, basically any linear regression t-test, that is what your null hypothesis is. That beta is equal to 0, that the slope is 0. In other words, it's just going straight across. All right, and there's no relationship between sleep time and memory. All right, the alternative is that beta is not equal to 0, that there is a relationship. You know, it says nowhere up here in the problem did we suspect this positive or we suspect this negative, so we go with not equal to. So that's your null, that's your alternative, okay? Now, what's the conclusion? Well, that's based on the p-value, and the p-value here is 0, or effectively approximately 0. What does that mean? Well, if the p-value is low, you reject the null, you have convincing evidence for the alternative. And so that's what we say. This p-value is less than 0.05, so I reject the null hypothesis. There is convincing evidence that, and then you restate the alternative, that beta is not equal to 0, that there is a relationship between the sleep time and the memory test score. Okay, so that is that. Okay, create the 95% confidence interval for the population slope. So our formula for confidence interval is going to be B, well, it's going to be this. It is going to be B plus or minus T star times the standard error of the slope. Okay, that is our formula. So B, what is that? Well, B is that number right there. And then that is our standard error of the slope right there, 2.09. Okay, and so there's B, there's standard, and that's T star. How do we find T star? Well, you find T star, in this case, it's 95% confidence. And so you would say this. You would say, well, with 95% confidence, so that means our interval takes up 95% of our distribution. Well, if 95% is inside, that means 5% has to be outside, and it's perfectly symmetrical. So these two parts contain 5%. There's going to be 2.5% on each tail, 2.5% on each tail. So how can we find this critical value there? By doing inverse T of 2.5%, which is 0.025. And then our degrees of freedom is our sample size minus 2. It's 48. Okay. So that's what we do. And so we would say, and so T, inverse T is in the distribution menu right above the vars button. So second vars, which is distribution, inverse T, 0.025. Our degrees of freedom is equal to 48, the sample size minus 2 when you're dealing with linear regression inference. And so, and there it is right there. Okay. And it's negative. We may, I mean, it's going plus or minus in the formula anyway, so it kind of doesn't matter, but technically it's 2.0106. And so that's how I got that. And so then you just multiply that times that gap gives us our margin of error. And then you say that plus that and that minus that, and there's our interval. Those are the plausible values for the true slope. Our slope in our sample is 12.51. These are plausible values for beta, the population slope. And so number 16 asks us to state the conclusion that should be drawn from the interval. And so there it is. In other words, to interpret the interval, number 16, I'm 95% confident that that interval captures the parameter, beta, which is the slope of the population least squared regression line relating sleep time and the memory test score. So there you go. All right, number 17, interpret the slope. All right, so the slope is the change in Y that we're expecting if X goes up by 1. So if we add one more sleep hour, we're expecting the test score to go up by 12.51. That's what the slope is. Okay, the slope, the way we interpret the slope, if X goes up by 1, this is what we're predicting is going to happen to Y. And it's positive, so we're going to say it's going to go up. So for number 17, we would say for each increase in 1 hour of sleep, we predict the memory test score will go up by 12.51. And if it was negative, we would say it would go down. But anyway, all right, number 18, interpret the standard error about the line, which is S. That is that number. That's the in essence, the standard deviation of the residuals. That's the average amount our predicted memory test scores will be off by when we use this model. Okay, so we would say predicted memory test scores, predicted Y values with this model will be off by 9.43 on average. So that's it for that. And then lastly, what percent of the change in score on the memory test is related to this model of score on the memory test and number of hours sleeping? That's what R squared is. R squared is the percent of the change in Y that can be explained by this model. Or another way of wording is the percent of the change in Y that can be explained by the change in X. Or in this case, the percent of the change in memory test scores that can be explained by the change in sleep hours. And that's that. And so this is just a statement for R squared, and R squared is given on the table to be 95.39%. And so that is it. Okay. And of course, your test will be extremely similar to this. So if you have any questions about this, please send it to me. And thanks for watching the video. Hope you have a fantastic day.